Yes. So once again 0.5.
No. The radius is the optimum value is 1.128. It's the radius in centimeter. We used the formula a square equal to pi r square, and from there we get this value.
The value should be close to this one, 0.669.
My value is 0.564.
So 0.564.
Yeah.
This is a optimal radius.
Yes.
564. Okay,
sir, maybe there will be more accurate if we recalculate 12. There's we found 20. If I use 20.1, 20.2, 20.3, that's why there will be more accurate if we calculate this one. I don't calculate for the 20.1, 20.2 like this one.
Okay. As I understand that 0.669 is closer to a real situation. Actually, the optimum, there is the optimum in the ratio moderator and fuel, but as usually the core is under moderated, so it's a bit shifted to under moderated, not over but under moderated. It's shifted to for this as usually not the optimum point. It's a bit shifted to the left. It's needed for good reactivity coefficient. It's needed. So as usually. So okay. Now just I recommend to state this value 0.669.
Okay.
Because need to check. I understand that there is an optimum, but if you get the optimum radius is a 5.654.5, it means that the core is a bit over moderated, so too much moderator that's needed, and that's not good. Okay, it's needed to check the values. So if you please send me back so your calculation, the file, these files, calculation Excel files, I mean, then of course send me back an input file. Okay, the input file. Okay. So it's need to keep me, because if I do some correction, if we look at the to do the further step, I need to have the last version, yes, of your files. So okay, we continue. So okay, I understand. So there you put your the nuclear densities. There is nuclear density of hydrogen and water for 0.75 mass density. The temperature is the same, and the radius. So keep the radius. Keep the values. This one values. Do not correct, because so need to check once again. Need to check once again. So yeah, it's uranium 35, uranium 38. That's calculation according to 82% here, 82%. So actually 8.95, yeah, grams per centimeters cubed. So okay. The next step. We start depletion. So I mean the burn up process, okay. Yeah. So the core yeah. One moment, please. Yes, this one not there. Okay. So our BVR here 1200. So the number fuel assemblies 163. The fuel assembly, each fuel assembly to consist of 312 fuel pins. Fuel. 18 control rods, fuel pins, and one central tube. So summation is at 331. Yeah, pins.
Yes.
31 pins, and 163. And depends on the fuel cycle. There are 4 types of fuels in the core. After the reloading process, in the core, there are fresh fuel designated as 0. Yep. 1 cycle, 2 cycle, and 3 cycle. So we can divide it into 4, 163, and so this is approximately 40. Yeah, 40
Yes.
fuel assemblies, fresh, 1, 2, 3. It distributed through the core with certain ideas. On this stage of our calculations, no matter how they distributed, because we use the cell calculations. Of course, it's play roles, but for calculation, the depletion, the burn-up process, yep, for K-infinity, it's play not so, this role not so high, and it's quite correct to do the modeling, to do the model of the core by cell model, the cell model. It's actually polycell actually. So 0, 1, 2, 3, right? And after the one cycle, cycle of burnout. Yeah. As usually, the duration of the cycle is usually 1 year. But so the last situation, they try to increase the length of the cycle, maybe 1.5 year or 2 years. And after the one cycle, this became 1, 2, 3, 4, and 4 withdrew, and put the fresh, and one cycle, next cycle. If we look this cycle 1, 2, 3, 4, and it's a 1. I try to draw dependencies of K-infinity of the fuel, actually of the fuel assembly, each fuel assembly, through the time. Yes, it's time. It's a 1 length of the cycle, 2 cycle, 3, and 4 this cycle. The K-infinity, I mean nu f sigma f over sigma a. Yes.
Yes, sir.
And when the fresh fuel, there is a fresh fuel, this point designated is K-infinity 0. Actually, K-infinity 0, you already calculated that you 1.3 with something, this one. Where is it? Oh, yeah, 1.6.
It's for 4.6% enrichment.
What is our enrichment?
4.6. Mine is
4.6, yeah. 1.59 K-infinity. So okay, so please me send. So your calculation of nuclear density, all the calculations keep in the Excel file, please, and don't hesitate to send me, because it's very easy to me to check if it's some problem, because for 4.4, 1.6, I think it's a bit too much. But please recalculate for the radius 0.669, this radius 0.669. But anyway, that's you already calculated this K-infinity. What's happened during the depletion? There is a small small, I mean, in time, it's quite steep reducing, and further there is a track line, just line. It's about excuse me. It's about 0.8. So the fresh fuel, you see, has a surplus neutrons, because the K-infinity is too much compared to 1. And further, after the second, third, and fourth cycle, that is they need to be supplied the neutrons from the fresh fuel. You see, and there is a reason of reloading this process, because during the reloading, the zero fuel, because without reloading, you see, the duration will be this one till 1 and must be stopped, and reload and further. But if there is a process of reloading, we can supply the depleted fuel by the neutrons from the fresh fuel, and that's why the duration of the fuel, duration actually of burn up, so we increase, significantly increased. Okay, understand? We increase it. If we it's time, K-infinity average. We will take K-infinity averaged equals 1.03 as K effective multiplication factor, excuse me. K effective equals 1. Understand?
yes.
So the cell program like a guitar, we calculated chi infinity, and we need to take some for leakage. But in case of Gitera, 1.03 get the best results. So 1.03, it means the multiplication factor equals 1. And when I calculate the average, yeah, you understand this, the meaning of the average, because before it's the same, this one, same, this one, the same, and this one the same. And look what's happened there. So so too much. I'm sorry. I'm. Yeah. Okay. The last not needed. This one. This one. Do the summation and average it, and we get the K infinity 0. We average it, and this one we average it, and this summation get this one point, and actually this one. So after the reloading process, it's there and further. This one, this one. It's a saw type curve, yeah. You have enrichment fuel, you have a fresh fuel, right? So you have a K infinity 0, this one that you already got. The question is, what is the burn up? What is the duration of the length? For your case, there are 4 cycles for both of you, the 4 cycles. And how get the duration of the cycle? The duration of the cycle depends when this when this point equals 1.03. If it's less, that means you should decrease the length. If it's more than 1.03, you should increase the duration of the fuel length. Did you catch it here?
Yes, I understand.
Yeah. So, okay, what are you going to do? So, first, you calculate K infinity 0 for a radius cell 0.669. This one.
Okay.
Number 2, you get this curve. Actually, it's a how to get this curve. If we look project, where is it? Cell in. Yeah, this hour. It's not needed this top. I don't know what's happened there. Maybe it's not the best choice. No. Name burn, the statement named the command burn. This one. So the first burn 10, 20, 20. It's a summation. This is summation. So it's a 50. With 50, it's at 100, and further you can go by 100, but not more. So don't use this step more than 100. So show there. This one. Yep. Yeah. This one. So air cell 0.669. So actually there, this fire get the K infinity 0, right? And this burn, QV, this one, 110, it's a specific energy release. So QV, it's a megawatt per meters cubed. In VVR 1200s, the specific energy release very close to VVR 1000. So need to check, but it's very close to 110, maybe 111. This one, check this. And the time. The first step is very small it's days. It's actually it's days. It's 24 hours.
Okay.
10 days, 20 in summation. 50 plus 50, 100, and further 100.
200 days altogether.
So, sorry.
Altogether 200 days or more.
Okay. And continue there. But sorry, need to be more. After each burn, you need to put the fire. Sorry, it's a bit. I forgot. Fire. Fire. I understand. Yeah, this is fire, and after the 10 days, after the plus 20, after the 30, after the 50, after the 100, and the further, and you will get this curve. Okay. This one. Nine. Number 2. Yeah. This is step number 2. Step 2. So get the curve. Get the curve. And you need so the question is what is the duration? What is the duration? And the same, it means the burn up. Yeah, because duration is so duration is time. Actually, time company, it means the company is a 4T cycle. T cycle, because we get the 4 cycles. The company and the burn up megawatt day. So megawatt days kilogram. Megawatt per kilogram. It is a specific energy release by unit of mass. Actually, it depends on QV. It's a constant. It's already really good. But QV actually from meters cubed, but it's the same. It's megawatts per kilogram. It's the same. And the burn up, it's very easy. You have a power of nuclear reactor, VVR 1200 for the thermal power. Do you know the thermal power?
34,000.
32.
32.
Yeah. 32 megawatts. Mass of fuel. What is the mass of fuel? How many tons?
It's almost around 180 tons.
How many?
180 maybe. One.
No, too much. 180.
Just a moment.
It's a kilograms. It's a constant.
Yes.
Maybe 70 tons. It's the mass of fuel. Total mass of fuel, not fuel assembly of the total mass.
$499 kilogram.
How many?
499 kilogram.
400.
400. Yes. 499. 499 kilogram.
Okay, that's your so you know this value. So it's a mass of fuel.
499 kilogram.
499.
Yes.
Yeah, but at the per fuel assembly, I mean the at the total core, you need the
Okay.
multiply 160.
163.
Yes, 163. Yeah.
Okay.
This one.
81 ton.
Yeah, and multiply it to T company. That you will get. And that is a burn up. This is actually burn up of the fuel. You need to calculate this one. This one. That's your target. It's your primary target for to the next Monday.
Sir, I have a question.
One moment. So I want to continue to finish. So get the curve. So you get this curve. This one. Yes, this curve. So the third step, so calculate time of cycle. So how to get the time of cycle? You will get this curve, and you need to first so choose the time of cycle. For example, start from time of cycle is 1 year. Time cycle, 1 year. And try to build this curve to so 1 year, 1 year, for 4 years. Actually, because it's very close to the line, so you can calculate the number of steps and to extrapolate this curve to the. So actually, you will get this point, and get the point year before, and year before. Do the summation and over 4. And you will get the chi infinity end of cycle. So chi infinity end of cycle, average chi infinity. It means the chi infinity of 4t cycle plus chi infinity 3t cycle plus chi infinity 2t cycle, and plus chi infinity 1t cycle over 4, 1 over 4. And this value must be equal 1.03. If it's true, that you get the time of cycle correct. If it's less, so it's less than 1.03, you need to, so it's too much burn up. It's needed to decrease the time of cycle. If more, so opposite, increase time of cycle. So B. So you need to get optimum time cycle. If you get the time of cycle multiplied by 4, that you get T company, and you can calculate the burn up. That's idea.
Yes.
So okay. Yeah, you get the sum about the method of first collision probability. As I understand, to Miro, you can upload the PDF or Word file. I don't know. Well, maybe it's so it's better to. So I need a space below because I will continue below and below and below. So please, your calculation. So your results put into the frame, or it's not, it's a bit left or right.
Okay.
So because we need a space below.
Okay.
So I will upload these pictures and you will continue. So if you have a question, I think no, because you as I understand, you understand. You catch the idea.
Yeah.
So.
So if we have some question, we'll ask you in the email.
By email, yeah, of course.
Yes.
Okay.
So that it is for today.
Thank you very much.
Okay. Thank you, sir.
Yeah. See you.
On Monday.
On Monday, yeah.
Monday.
So please write me a mail. So maybe
Remembering you.
in the Monday morning.
Okay.
Please
Okay.
write me. Okay.
Okay.
So. Okay. Thank you all.
Have a nice day,
I will-
sir.
I mean,
Yeah.
Thank you.